Hello again. In this video, we are going to evaluate this integral right here that will help us to find the volume between this sphere and the cone below it. So I will zoom in. And this is really just, if you know how to evaluate a double integral, if it's given in front of you, that's all this is. There's some, you just gotta be careful with your arithmetic in this one. It's honestly kind of annoying. But let's just go ahead and jump right into this. So the first thing I need to do is distribute this r into both pieces. So I get the integral from 0 to 2 pi, and then the integral from 0 to root 2 over 2 of, when I distribute that, I get r times root 1 minus r squared minus r squared. Now, um, this piece is easier to integrate, and this piece takes a little bit more work. Just for the sake of, I will do it do it quickly first, and then I will show you how to do it by using u sub, in case you would prefer u sub with my dr d theta. Okay, so this is the integral from 0 to 2 pi. What I want you to see is that the u sub lines up. What I mean by that is I've got r squared and its derivative r. Or sorry, I've got 1 minus r squared and its derivative r, or at least a multiple of its derivative. So what's this going to go to? It's going to go to 1 minus r squared to the 3/2 power. I need to multiply by 2/3. That's to balance this. And then I need to multiply by negative. And then 1/2, because that's what the derivative of this thing would be. That we would have a 2 in it instead of just an r. And then these guys are going to cancel. And then minus 1/3 r cubed, evaluated from r equals 0 to r equals 1. I'll write root 2 over 2. I'm just going to leave it as a half. So let me quickly scratch out the u sub. So if you prefer to do u sub, I did all the work here in red. U is 1 minus r squared, du is negative 2r, negative 1/2 du is r dr. That's going to replace this and the dr that would be attached if I was integrating this on its own. So the integral of this is going to be negative 1/2, that's this, du, the other part of this, and then the rest of it is u to the 1/2. That's this piece right here. So when I integrate that, 1/2 times 2/3, that's the flip of this, times u to the 3/2, which gives me negative 1/3, blah, 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 which matches over here. So hopefully you're cool with that. And then I'm actually missing something on this. I need to have a d theta. So I may as well say it now. There is a way to quickly do the outer integral because there are no thetas in here. And I'll kind of go over that later, but I'm not going to do that now just because I think I'd rather focus on just evaluating this integral. Actually, I'm going to simplify this, change this out in one little way, and that is, I'm going to do that by looking at this problem. There's a lot of symmetry here. There's a lot of radial symmetry. So what I would argue is that if I were to slice this thing like with a plane, I guess slice it through the YZ plane right there, then the front half and the back half would be exactly the same. So, and notice that would be like slicing the region in half there, which would be going from 0 to pi. Or I guess I should say, if I was, that same, it would also work elsewhere. But anyway, what I'm trying to say is that with this thing down here, if I want to get rid of this 2 pi, I can just change it as the integral from 0 to pi and then double the integral. We've done some tricks like that before, and I'm going to do that just to demonstrate it and also to make this a little bit easier to do. The next thing I'm going to do is recognize that there's an over 3 and an over 3 here, and really write this as 2/3. And then I've got minus 1 minus r squared closed to the 3/2 minus r cubed evaluated, that's all of this, maybe I'll bracket this, from r equals 0 to r equals root 1/2 with a d theta on the outside. So from there, I need to evaluate it for these two spots. So this is 2/3 integral 0 to pi of. All right, so I'm doing this entire thing, so it's going to be this. I'm going to do it like this. I'm going to do a bracket minus a bracket. This is going to be r equals 0, and this is going to be r equals root 1/2. Just showing that so that you can keep track of everything I'm doing. So it's minus 1 minus, when I plug r equals 1/2 into r squared, r equals root 1/2 to r squared, I get a minus 1/2 here. And that goes to the 3/2. And then minus r cubed, so I get minus the square root of 1/2 cubed. Correct? Yes. Okay, so, and then I come over here and I plug in r equals 0. So when I plug in r equals 0, I get a negative 1. And that's this, when this is 0, it's negative 1 to the 3/2, so that's just 1. And then when I plug in r equals 0 to this, I get minus 0. So the second, the r equals 0 is a lot easier to deal with here. So now I just got to simplify this and simplify some of this stuff over here as well. And don't forget we have our d theta. So this is 2/3 integral. All right, what do we have here? This is a half. Notice this is 1/2 to the 3/2, and it's negative. And then look, this is actually also 1/2 to the 3/2 because it's cubed and square rooted. That's the same as the 3/2 power. So this has a negative and that has a negative. So they're actually minus 2. Actually, I'm going to go, there are negative 2 1/2 to the 3/2. Hopefully you see that. We can rewrite this as that. And then there's a double negative plus 1, and then my d theta. So from here, I just have to integrate this with respect to theta. Remember, our bounds are now 0 to pi. So since this is a constant with respect to theta, this is 2/3 times negative 2 times 1/2 to the 3/2 plus 1. Maybe I should switch those, just makes me happier, times theta evaluated from theta equals 0 to theta equals pi. And you might be used to just saying, all right, I go and I multiply this by that, and that's fine. But when I evaluate that, this times the theta gives me this term times theta, and then this times the 0 just gets rid of everything. So what do I wind up getting? I wind up getting 2 pi, sorry, not theta, over 3 times, I like to write this as 1 minus 2 times, we could go the square root of, I'll just write it to the 2/3 power, of 1/2 to the 2/3 power. Not 2/3, 3/2. So this is acceptable. This is good enough, but I'm going to show you one way that this would simplify. I could write this as 2 pi over 3 times 1 minus. All right, the 3/2 power is really, minus 2 times the 1/2 times 1/2 to the 1/2, right? And what is this? Like this has a total power of 1, 1.5, add to this 3 over 2. So then you can see when I simplify it like that, those guys cancel there. And then this 1/2 to that power there gives me 2 pi over 3 times 1 minus, this is just the square root of 1/2, or it's the square root of 2 over 2. So, boom. Whew, that was a long one. Done with that. I sort of explained a lot there, so I think that you might be able to get through that a little bit quicker. But really, the big takeaways are, I can do this integral of top minus bottom, dA, or double integral of top minus bottom over a region to figure out volume. And 2, when I've got all these x squared plus y squareds, or when I've got a region for which it's easy to write using polar coordinates, oftentimes we want to switch to polar. Sometimes, usually we hope that we get both. We usually hope that it converts easily, and that the region is good. And sometimes we stay in rectangular coordinates. So hopefully you're cool with this. Hopefully you're cool with all this arithmetic. And I will see you next time. Bye.